Hello, I'm David Lindell, and I'm presenting BACN, Band-Limited Coordinate Networks for Multiscale Scene Representation. Coordinate networks are fully connected neural networks that map input coordinates to an output signal value. For example, pixel values in an image, neural radiance fields, or 3D shapes through a signed distance function. Usually, coordinate networks can represent a signal continuously using far fewer parameters than conventional representations, such as arrays or voxel grids, which require fine discretization. However, coordinate networks are black boxes. Behavior at unsupervised input coordinates is difficult to predict, and current representations are not scale-aware, so we cannot easily ensure that low-resolution network outputs are properly anti-aliased. We propose band-limited coordinate networks, or BACN, to address these limitations. This architecture has an analytical Fourier spectrum, which allows constraining outputs of the network to desired resolution scales. Other coordinate-based networks like Siren and Fourier features represent signals at a single scale. The MIPNERF architecture allows controlling the output resolution by adjusting the positional encoding after supervising across multiple scales. Other multiscale methods use octrees or hierarchical representations, but these architectures are black boxes with no guarantees on the band-limited resolution of multiscale outputs. Our work differs because the network bandwidth is explicitly constrained. To this end, we build on multiplicative filter networks, or MFNs, which interleave linear layers and Hadamard products between sign activations. We developed the theory of MFNs significantly with new tools to manipulate the Fourier spectra of these networks and a new initialization scheme for training deep networks. Consider fitting this 1D signal. Supervising with Siren, or Fourier features, results in artifacts between the supervised points caused by non-zero high-frequency components shown on the right. Using BACN allows band-limited interpolation between supervised points. We can also perform low-pass filtering by lowering the network bandwidth. The inputs to the network consist of several layers with assigned nonlinearity. The first of these inputs is fed into a linear layer, and then this is combined with the following input layers via Hadamard product. Outputs are extracted by applying linear layers after the Hadamard products. To set the network bandwidth, we initialize the frequencies of each input sign within a specified range. In the paper, we derive analytical expressions for the representable bandwidth at each output layer, and we show that these are simply multiples of the input frequency ranges. Since all outputs of the network have a constrained bandwidth, we can supervise all outputs on a signal at a single scale, and the network learns band-limited representations. We train BACN and the other baselines to represent an image of a lighthouse. Since Siren and Fourier features are not scale-aware, downsampling the output without an explicit anti-aliasing step results in artifacts due to high-frequency components. MIPNERF learns anti-aliasing after supervision at multiple scales. Outputs of BACN are automatically band-limited and anti-aliased. If we finally sample the network outputs at 4 times the trained resolution, all outputs except BACN have artifacts caused by high frequencies in the representation. BACN automatically performs a band-limited interpolation equivalent to zero padding in the Fourier domain and produces a predictable output at these unsupervised input coordinates. We compare BACN to NERF and MIPNERF on a multiscale dataset of synthetic images. While MIPNERF achieves the best performance, BACN outperforms conventional NERF models that are not scale-aware. Moreover, for low-resolution outputs, BACN uses a fraction of the parameters. Finally, we train BACN to fit a signed distance function estimated from a mesh and show the resulting multiscale representation and Fourier spectra. Fine details are preserved in the high-resolution output, while low-resolution outputs provide a simpler, smoother shape representation. Compared to neural geometric level of detail, low-resolution outputs of BACN are much smoother because their Fourier spectra are constrained. In summary, our work takes steps towards making coordinate networks interpretable and scale-aware. We believe BACN may be useful in many pipelines in vision and graphics for representing and optimizing signals while providing interpretable and transparent behavior.